Can people hear me? Cool. Can someone in the chat let me know if they hear me or not? I'm actually not sure which microphone. Can people hear me? It's connected to. Well, okay, cool. All right. So, cool. Can someone in the chat let me know if they hear me? Okay. So, for those that have been on one of these live streams before, you know the deal. But basically, it starts off with like a maybe like 1 to 2 minute delay, and then eventually, as it because I'm recording this on YouTube Studio, and I think that starts a kind of a buffer. So the delay between what I'm saying versus the time you hear it gets longer and longer and longer. So almost by the end of the session, I'm you guys are like 20 minutes behind what I'm actually saying. But the chat is instant. So if there's something, oh, you hear me twice? I think it's because one of these. Let's see. Um, like how bad? Hear me twice or hear me clearly? Uh, it sounds. You guys are like 20 minutes behind what I'm actually saying. Sounds all right to me. But the chat is instant. Okay, so I'll continue on, but the chat is instant. If there's an issue or something, let me know. Okay, cool, it's clear. Okie dokes. So what we're going to be doing today is I'm going to copy and paste that link one more time for you guys. Get link. So we are, okay, cool. Thank you, King Buck. There's a lot more people on this stream than the last one. Okay, so thank you, everybody. So what we're going to be doing is we're going to learn about support vector machines. Support vector machines are a machine learning algorithm. So we're going to learn about them through some slides just to understand how they work. And we'll be going mostly over the intuition of how they work. Later on, if you want, you can actually go into the course and see the more mathematical theory lectures. So we'll be going over the intuition lectures together. I think if you go over the intuition lectures with me, you should kind of understand how they work. Support vector machines are one of the more complex machine learning algorithms that we cover, but the fundamental ideas behind them are actually pretty straightforward and very clever. So, just in case you haven't done it yet, the data is available here. Whoops, that's not right. Remove. Wrong link. Data is available here. Let's copy this link. Link copied. Okay, so download that data while I go through some slides. That data contains some data about wine, and we'll be attempting to see if we can use support vector machines to classify legitimate wine versus fraudulent wine, and we'll talk about what that means later on. But let's get started, and if you have any questions as we continue, just put them in the chat and I'll reply. And if it's kind of a pressing question, I'll reply directly in the chat. And let me get you guys the link to the slides as well. I'm going to start putting this over. Just so you can kind of tag along with me. Done. My slides. All right, so you have the slides as well. Keep in mind, these slides also contain the history of support vector machines. I'm not going to go through that because you guys can kind of read it on your own. It's probably more interesting just to read a book or something on it. It's basically for kind of the 5-second history. Vladimir Vapnik invented these in the 60s in the Soviet Union, and he kept developing it for like almost 35 years. He just kept working on it, and working on it until he basically figured out the kernel trick, and then also along with I think she's from the Netherlands. This other researcher called Karina Cortez. Okay, so what I kind of want to do here is go through just the intuition. That way we know enough that we can go through the project together and then see how they work in scikit-learn. If you have any questions as we continue on through this, just put them in the chat. I'm starting at slide 20. I'm starting at slide 20. Okay. And also as a quick note, as the buffering gets worse and worse, you may want to rewind like 5 minutes and watch it. That is, rewind the YouTube video. It's due to the DVR effect that I'm like recording this. If you try to watch it like right in line with me, sometimes it buffers and buffers and buffers. Okie dokes. So I don't see any questions here, so it looks like we're kind of good to go. I'm going to start kind of walking through this. Support vector machines. So we're going to talk about hyperplanes and margins. The whole idea behind support vector machines is data's up there in the link. Okay, so support vector machines. The idea behind them is actually super simple. It's basically if you were to have two classes kind of grouped together, were you able to draw a line that separates them? So what does that actually mean though when we're dealing with way more complex stuff? So we're going to slowly build up to support vector machines. We're going to start by talking about the maximum margin classifier. This is essentially the classification technique that was invented like 50s, 60s, and then it slowly got progressively better with support vector classifiers. Almost at the exact same time as max margin classifiers, they invented support vector classifiers, but then it took a long time to develop support vector machines with the kernel trick. So I want to start off by beginning to understand what the term hyperplane means, because we don't hear it too often when it comes to lower dimensions, but typically it's something we talk about a lot at higher dimensions. I'm sorry for the like weird light, but oh well. All right, so what is a hyperplane? In n-dimensional space, a hyperplane is a flat affine subspace of hyperplane dimension n-1. That is the official definition, and if you read ISLR, it's what it's going to say there. So what does that actually mean in like layperson's terms? It means essentially if you're dealing with n number of dimensions, just go one dimension down, and then sorry, someone is. Okay. So, what was I saying? Oh yeah. So, if we have a n number of dimensions, just go one dimension down, and that is now your hyperplane. So, if you're dealing with one dimension, a hyperplane is just a single point on that line. In 2 dimensions, that would be like a plane, right? x1 and x2, or x and y. Hyperplane is just a line there. And then 3 dimensions, it's a flat plane. So in 3D, hyperplane is 2D. So let's go through some examples of this. So 1 dimension, that means we could, in theory, if we start connecting this to data and features, 1 dimension, we have 1 feature, right? Which means if you have 1 feature, kind of 0 features, so to speak, or a hyperplane, it's just a single point somewhere on that line. And so here's the thing to note right now. As we reduce this to the simplest case possible, that means in 1 dimension, the hyperplane is a single point, and I can see, I get the pointer out, on either side, I have now separated out this feature, right? With just a single hyperplane, now I can say I have one group over here on this side, one group over here on this side. And that's kind of the theme behind these hyperplanes. Same thing for a 2-dimensional hyperplane. It is a line. So it's kind of like if we had one feature that was a line, now that's the hyperplane for the next set of dimensions. Same idea here. I now separate this out, and right now I'm just considering feature 2 or feature x1, feature x2. I've separated this out that it can split into this half and this half, and that's the main idea behind support vector machines. So super simple idea, much harder to actually do this mathematically, but the intuition is simple. Can I draw something that separates out classes? So in 3D dimensions, now the hyperplane is 2-dimensional, right? It's a 2D plane. And same idea, obviously it gets harder and harder to visualize this, and we're kind of at the max of what we can visualize because I can't draw in 4 dimensions. But we can see here that now this plane, if it were to extend out continually along these 3 dimensions, it essentially separates out everything kind of above the plane and below the plane. Any questions on what a hyperplane is? Put them in the chat and we can clarify that, but should be pretty straightforward. And as I keep saying, the main idea behind support vector machines is we can use these hyperplanes to create that separation, right? What side of the line do you fall on? What side of that point do you fall on? What side of that plane do you fall on? And in real life, we're dealing with hyperplanes that are like in 8 dimensions or higher. It's impossible to visualize and almost impossible to understand, but as you can see, as it progresses, the idea remains the same. You can always be separating this out. So, new points are going to fall on one side of the hyperplane based off the features, and then we assign it the class that way. So let's imagine a data set, and it's much easier to understand support vector machines if you don't start on something like 7 dimensions, but you reduce it to the simplest way possible. So we're going to go all the way down to 1 dimension, which I should say is really, when we think about dimensions, we're really thinking about features, because we want to link this to the real world data sets. So imagine a data set with 1 feature and 1 binary target label. So for example, baby chicks, it's actually kind of notoriously hard to sex them as male or female once they're born. So you can read at the Wikipedia page on this. It's kind of interesting, but basically they like squeeze the little baby chicks till poop comes out and then they can see the genitals. But for our example, we're going to pretend that their weights are very different. And then classified by male or female based on that weight. What would that look like visualize? There's a quick question in the chat I'm going to address here. Will we learn how to choose the correct hyperplane? Say in 1D? Yes. So the users themselves do not choose this hyperplane. It is going to be scikit-learn that chooses the correct hyperplane. And we're actually going to cover how we choose this correct or best fitting hyperplane. And that has to do with the margin factor. So great question, and we'll see how that works in just a second. Okay, so right now we're dealing with 1 dimension, that is 1 feature. And we're going to place these points along the feature. That is, we have a feature X, that is the weight, and we have a class. The class is the label Y. That is what we're trying to predict. So male and female are not a feature, it's just a class that we're trying to predict. So what I would like to do is, in the future, I can take a little baby chick, weigh it, and then know if it's male or female. So I can know what farm to ship it to. Okay, so place these points along the feature. And so far, if I'm looking at this, it's kind of obvious what I should do, right? I should probably place some sort of separating point between these, and then I will be able to say, okay, depending on what side, if you're greater or lower than this particular weight, I'm going to classify you as male or female. So notice in this case, the classes are perfectly separable. This is totally unlikely in real-world data sets, so we're going to have to expand this later on to understand how to deal with non-perfectly separatable classes. But for right now, let's pretend these are perfectly separable. So, as I keep mentioning, the whole idea behind support vector machines is to create that separating hyperplane between the classes. So what I'm going to do here is I'm just going to put a weight down, and then a new point is going to be classified based on what side of the point they land on. So if I have a new baby chick and I weigh it, and it ends up being a weight that falls on this side of the hyperplane, well, I'm just going to say, okay, I'm going to predict that that baby chick is male. Because historically speaking, I already have all these other chicks that have been weighed and sexed as male, and I have the separating hyperplane, so I understand that most likely this point is going to be male. And we'll talk about more complex things like multi-class, etc. later on. But yes, this will all work with multiple classes, multiple features, etc. But to really understand what's happening, it's best to kind of reduce it to the base case. So, same idea. I have a new chick. It weighs about this much. I'm going to say, well, it falls on this side of the hyperplane, and it's going to be then predicted to be female. Is separable another word for discrete? I would say, well, discrete tends to imply that it's like non-continuous, right? So I'm definitely not going to say separable is another word for discrete, but we are dealing with classification in this case. So you can think of classes being separate, if that helps you, Julia. Okay, so now it sounds kind of funny to say your chat names. King Bach, you were asking, how do we choose the correct hyperplane, right? So that's essentially the question I have here. How do we choose where to put this separating hyperplane? Because in theory, there's actually many options that perfectly separate out these classes, right? If the goal was just to choose a hyperplane that can perfectly separate out my historical training data, any of these orange lines, or orange points, I should say, will perfectly separate them out, right? This line right here is going to perfectly separate male versus female. But intuitively, we just kind of know somehow that this is probably the ideal one, right? The one that's kind of in the middle of these two, versus kind of having this one all the way up against the male class or all the way up against the female class. So now we have to think, mathematically speaking, at least intuitively, can we visualize this? What gives us the intuition that we want to place the hyperplane there instead of choosing one of these other ones? So which of these is the best separator between the classes? And so when you're reading the actual publication by Vladimir Vapnik, he's kind of describing this as picking out the best separating hyperplane. So what we're going to do is we're going to use the idea of margins that extend off this hyperplane. And what we want to do is figure out what's the separator that is going to maximize the margins between the classes. Keep in mind, right now we're only dealing with perfectly separable classes. We'll talk about non-separable cases in just a second. But this is how we choose the best hyperplane. It's the one that's going to maximize this distance from the hyperplane point to the margin, where the margin is going to be touching right up against the first instance of the class. Now, is this a support vector machine yet? Absolutely not. This is not a support vector machine. This is kind of the grandfather, if you will, of a support vector machine. It was the first development in this early 50s, 60s, and this is known as a maximal margin classifier. It's a super simple idea. What you're going to do, choose a hyperplane, expand the margins until the margins get maximized. Now we have a question in chat. What does soft margin mean? Good question. We'll cover that in just a second. So you guys are kind of thinking ahead. That's good. So we'll get there. But the same idea of maximum margins applies to n dimensions. So let's think about this in 2 dimensions. Let's say I'm taking these little baby chicks and I also measure their height and their weight. Obviously, this is very ideal data. It's perfectly separable. So let's imagine this in a 2D feature space. These are typically the examples you'll see if you go to Wikipedia or whatever. They show this kind of nice situation here. Recall, in 2 dimensions, a separating hyperplane is a line. And it's the same idea. What side of the line do you fall on? Or what side of the hyperplane do you fall on? And we're going to classify you depending on your feature of weight and height. So if I have a new chick with this weight and this height landing over here, it falls on this side of the hyperplane, so I classify it as male. Now, back to King Buck's question. There's multiple hyperplanes again that perfectly separate out these classes. So look, all these lines that I've drawn here separate out the classes absolutely perfectly. But again, we kind of have this intuition that this line looks kind of the most intuitively correct, so to speak. So what's actually happening here? It's the same idea. I want to choose the line that is going to maximize the margins. So I choose my hyperplane and I keep testing out a bunch of different hyperplanes, and there's, mathematically speaking, kind of optimal ways to do this, almost like fitting a linear regression, that I keep tilting it until I get this margin coming off, and then it's going to come into contact with the data. So instead of 2, I'm not sure why 5, but you can have as many classes as you want with support vector machines. Obviously, for these visualizations and for understanding support vector machines, much better to just start with 2 classes and 1 feature or 2 features. But yes, this will work for n number of classes, so to speak. Okay, so again, this is not a support vector machine yet. This is a maximum margin classifier. You should also note that in theory, each data point is a 2-dimensional vector where each of these data points contains weight information and height information. Weight information and height information, that's 2 features. That could be thought of as a 2D vector, right? So now we start thinking of this idea, why they're called support vector machines. But the idea, we're not actually at a support vector machine yet, but if you're thinking about where this name comes from, the data points at the margin support the separator. So these are known as support vectors. This is technically still a maximum margin classifier, but I want you to start getting the idea of, I kind of like to think of them as like little vectors holding up the margin themselves. But that's why they're called support vectors, because, and this is kind of, if you look at the course, we talk about this mathematics later on, but in theory, it didn't actually matter where any of these points were. It only matters where the support vectors are. So that actually will make the mathematics of this much easier to compute, because you only have to end up computing the margins based off these support vectors that it first comes into contact with. We're not going to focus on the mathematics behind this too much right now, but just keep that in mind, that the idea of only worrying about the support vectors you come into contact with will help you computationally speaking. All right, now, real life, the classes are not perfectly separable. So what happens if the classes are not perfectly separable? You're going to have a problem now, because it doesn't matter. We're kind of thinking back into 1D. Can you kind of find a point that is going to separate out these classes? No, you're going to have to allow for misclassifications. We're not going to be able to separate without allowing for misclassifications. You guys can vote whether or not you like me answering the questions during the slide talk. I don't mind answering it. We're not able to separate without allowing for misclassifications, right? So notice the classes here are not perfectly separable. And there's no point I can choose along this line without accidentally either mislabeling this blue point as male or this historical red point as female. So we can already start thinking that I have what's known as a bias variance trade-off depending on where I place the separator. And this is where we kind of start seeing the idea of what side of the margin are you falling under for classification. So for one feature, this classifier essentially creates ranges for male and female. So again, if I chose this point as my hyperplane separator, everything that's on the right is going to be classified as male. Everything that's on the left is going to be classified as female. So that means if I take a look at this point, it's going to be classified as female instead of male. So I'm allowing for one misclassification. And I could put the hyperplane all the way over here. And if you take a look, this also is going to be just doing one misclassification. So both this hyperplane and this hyperplane allow for one misclassification. So when we think about this, their performance is technically the same, right? They're both misclassifying only 1 point. But clearly, this point, this hyperplane in the middle, is probably still the better fit than this point right here. Because we can kind of think of this hyperplane as fitting too much or picking up too much noise from the female points. I'd rather have something more in the middle and more generalized for future points. So, a new test point could be very close to the existing female points, but if I chose this hyperplane, it would have gotten classified as male. So I want to figure out what kind of trade-offs am I willing to get in order to figure out the best hyperplane. And this is kind of the sticky situation we have with maximum margin classifiers if we don't allow for any misclassifications, right? So here, in this particular case, I'm going to allow for misclassifications as I figure this out in order to, hopefully, for new future data, be able to have better bias. And so this is the idea of the soft margin. So the distance between the threshold and the observations now is the soft margin. And what's the difference now between the maximum margin we just talked about versus the soft margin? Well, now the soft margin is going to allow for points to be inside the margins. Recall, previously, for maximum margins, I just wanted to maximize the margins until they finally came into contact with a vector. Now with the soft margins, I'm going to allow the margins to continually expand, and I'm going to set some limit of, hey, actually, I am going to allow some points to be inside the margins in order to get a better fit. And so the soft margins allow for misclassification inside the margins. That is how we move from a maximum margin classifier to something known as a support vector classifier. There's many possible threshold splits if we allow for soft margins. Essentially what we're going to do is use cross-validation, a train test and a test set, to test a bunch of different soft margin values to figure out the best hyperplane. So let's think of this in 2D, just so we can expand on this. So two-dimensional soft margin example, we have, again, the weight and height, two features, two classes, male and female. The data set is technically perfectly separable. Why is that so? Because if I used a maximum margin classifier, take a look at this. I would end up with this hyperplane. The margins are tiny because I don't allow for any misclassifications, but this is the way a maximum margin classifier would have separated out these two classes. But obviously, if a point is like over here, or over here, or over here, it's probably a female point, not a male point. So we want this to be a little more flexible for misclassifications, essentially have softer margins. So I don't want this kind of extreme maximum margin classifier. Instead, I'm going to use what is known as a support vector classifier that has soft margins. Key point to realize here, I'm calling this a support vector classifier. It is actually not yet a support vector machine. We're still not at support vector machines, although we have done a big leap in that right direction. With the addition of soft margins now, I can allow for the misclassification of this one guy. And really when we say misclassification, all I'm saying is I allow a certain number of points to be inside the margins. And this is technically actually a support vector because anything that's in the margins or touching the margins is supporting the hyperplane's decision of where it should go. So this guy is going to get misclassified, but we're okay with that because we want something that is generalizing better to new incoming data. And now I get kind of these two sides for my class calls. And that's the support vector classifier with soft margins. If anyone has any questions, you can post in the chat. I think now would be kind of a good time to post that. I can answer those questions. But that is the support vector classifier. We're not yet at support vector machines. Okie dokes. Put my glass back on, take some water. I'm going to see where you guys are. I don't see any questions yet. Okay, I didn't see any questions on support vector classifier soft margin, so I'm going to continue on. Okay. We're almost at support vector machines because we've only visualized cases where the classes are easily separated by the hyperplane in the original feature space. Allowing for some misclassifications still results in reasonable results, but here's the thing. What would happen in a case where a hyperplane performs poorly, even when you allow for a ton of misclassifications? So what do I actually mean by that? Imagine this case. And now we're in trouble, even if we use soft margins. Notice, a single hyperplane here won't separate out the classes without a lot of misclassifications. And I'm no longer using weight as some feature. I'm kind of just pretending, okay, I have some feature here, and here's my main problem. The males are kind of clustered around the center, and then females are at the edges. There's no hyperplane I can choose that is just not going to perform really poorly. They have at least, Jesus, they have at least 3 or 4 misclassifications, right? So it doesn't matter how we think about this. All these hyperplanes are just going to perform awful. And then if I think about this, what it would look like in 2 dimensions, now I have this problem. Imagine if it was male-female with this sort of split. There's no line I could choose that is going to split out this effectively. And sometimes people like to see this and think, oh, I have an idea. What about multiple hyperplanes? Even with multiple hyperplanes, you'd have to have a line here, and then another line here, and then another line here, and then another line here. You'd have to start computing like 4 hyperplanes, the margins for them, then the zones of the hyperplanes per feature. It's just too complicated. And sometimes people get that intuition here, like, oh, why don't I just have a hyperplane here and a hyperplane here? But as you expand to more dimensions, that computation just becomes totally unreasonable. But you're kind of on the right track with thinking there must be some kind of higher space thing I can do. So what we're going to do is we covered maximum margin classifier and we covered the support vector classifier. Now it's time to move on to support vector machines. Support vector machines was Vapnik's solution. That is Vladimir Vapnik, the original Russian researcher who figured out all these support vector machines calculations. He figured out, oh, I can use something used a kernel to project the data to a higher dimension in order to use a hyperplane in this higher dimension to separate out the data. Recall that the hyperplane can be solved for in different dimensions, 1D, 2D, 3D, etc. And so what we're going to be able to do is use a higher dimension to separate out the data. And I remember at first, when I first learned about this, it almost seemed like a black magic. But if you visualize this in the simplest case, it's actually very simple to think about projecting something to a higher dimension. And maybe you've seen those examples. Maybe you, I can kind of show this in my stream here on the bottom corner. But essentially what we're going to do is instead of having like a flat plane like I have here, we're going to end up like projecting it or bending it upwards to figure out a hyperplane that can separate this out. It's almost like in all those sci-fi movies where they say like, oh, here's a wormhole, just fold it and then you can travel here, etc. Oh, sorry. Let me try fixing that real quick. Hopefully that's a little better. Although I do have this light up here, so I don't know how annoying that is. But maybe you saw that little example of me separating this out. You get the idea, I think. Anyways, that curtain thing was also bugging me, so that's why I changed it. So let's talk about now support vector machines. And then once we understand support vector machines, we can actually code this out with scikit-learn. Okie dokes. So, kernels. Kernels allow us to move beyond the support vector classifier and use support vector machines. There's actually a variety of kernels you can use to project the features to higher dimensions. Some kernels are, mathematically speaking, way more complex than others. And so we're going to explore this through kind of simple kernels. So what I want to do real quick is I'll talk through support vector machines, and then we'll kind of go through these questions that I'm getting right now. Okay, so recall our 1D example of classes not easily separated by a single hyperplane. What we're going to do here is let's imagine I have some feature X, and then I have now two classes, people that defaulted on their loan and people that did not default on their loan. So I'm trying to predict whether a future customer is going to default on their loan based off some feature X. And we can think of this feature almost like an income feature. People that have kind of close to a zero, let's think of this feature as a change in income. People that have very little change in income are able to plan their finances out well, and so they're probably not going to default on their loan. Even if their income shrinks a little, stays the same around zero, or increases a little. Now typically, and you kind of see this in real life, people that have major drastic negative changes in income are going to default on their loan because they lost a bunch of money. But people who also have great increases in income sometimes start spending beyond their means, and then suddenly maybe someone loses a job or somewhere and they took on way too much debt and they default on their loans. This is very simplified, but we're going to kind of pretend this is to be the case for this very simple data set. So if you have kind of no change in income around zero, you're not going to default on your loan. If you win the lottery, and you kind of hear a lot about this, people that win the lottery go bankrupt a lot of the time. So you get a huge change in income, you're going to default on your loans because you live beyond your means. And also if you lose a bunch of income, you're going to default on your loan. So how does the kernel actually work to project this onto another dimension? And when I say dimension, it sometimes is confusing to new students, but really it's just some other like plane or feature. And what we're going to do is we're going to use probably the simplest kernel to understand, which is the polynomial kernel. And all the polynomial kernel is hey, you have a feature X, try a polynomial. Polynomial is being try squaring it, cubing it, to the power of 4, etc. So let's imagine that we have this income change. It's centered around 0, goes to negative 10, 10, etc. And then what we're going to say is take a polynomial kernel and essentially take that feature and check it out with x squared. So this is the kernel. What it's essentially doing, which is to say it's going to project the original features to some other or higher dimension. It's not always polynomial. Keep in mind there's many kernels to choose from, some more complicated than others. But in this case, we can see that if I project this to x squared, in a sense, now I have two features, my original x and my x squared. So with two dimensions, my hyperplane is going to be a straight line, right? So I could create a hyperplane after projecting this to a higher dimension. This is a support vector machine, and this is the main idea behind it, how it works. All it does is it tries to figure out, is there some other higher dimension I could project this to, and could I find a hyperplane that separates it out? This is a very simple example where we go from one feature to two features. I think that's the easiest to understand. You get beyond this, it becomes almost impossible to visualize like 7-dimensional features expanding into like 49 features. But hopefully this is, pretty straightforward. All we're doing is we take some sort of kernel operation, the simplest to understand is polynomial, and then I can find a hyperplane in that higher dimensional space to separate it out. Like this. So what would this look like for new incoming data? Recall, I don't actually have the x squared feature, I only have my original x feature. So we use the kernel projection to evaluate new points. So let's say we have a new person coming into our bank and they have this income. What I'm going to do is say, okay, this income, project it up here using my polynomial kernel of x squared. Now, in this new higher dimension, what side of the hyperplane are they landing on? Well, they're landing on the default side, so I'm going to classify this as default, which technically also classifies this guy down here as default. And that's all there is for support vector machines. This is no longer a support vector classifier, it's a support vector machine because I am using some sort of kernel to project it to a higher dimension. Now let's imagine a two-dimensional feature space where a hyperplane cannot separate effectively even with soft margins. This is kind of a simplified example of what we saw earlier, right? I have kind of this outer circle of points and this inner circle of points. And this is what's going to happen, essentially. If I think of those points, I can draw this myself, actually. Hopefully this isn't too bad. We'll see. But I didn't plan on drawing this myself. But what I'm going to do is kind of draw what we have here. Let's see if I can take the camera. We'll see how well this works. You see here I have a bunch of X's and circles on this piece of paper. So if I have this piece of paper and I think about it being x1, x2 flat like this, what I could do is eventually curve this space and kind of curve it like in both directions. Hard to visualize this. But if I curve that space, I could take a hyperplane and slice this piece of paper in half, and then it would only take the x's that are kind of on top and keep the o's that are on the bottom of the paper. Not sure if that was the best explanation. Maybe you can tell me in the chat if that actually made sense. But I'm going to show it visually. That's kind of what I'm about to show in the slides. It's just, it gets harder and harder to visualize these things, especially when I'm dealing with two-dimensional slides. But that's exactly what I'm about to show in the slide, so hopefully that kind of helps out. So what I'm going to do is use a support vector machine to transform this, and I'm going to go from 2 dimensions to 3 dimensions. Essentially kind of curving that space. Sometimes people like to think about this as like having a piece of tablecloth with a bunch of like ping pong balls on it and then tossing it up in the air. And then while it's in midair, you find the hyperplane that can slice these. Okay, I'm glad some people are responding in chat that they got that. I don't know how janky that explanation was. But hopefully it's starting to get you an idea of what the kernel trick is actually doing. You're able to project things to a higher dimension. We're right now dealing with the polynomial kernel. That's the simplest one. You can get way more advanced than that. And you may have heard of support vector machines. I'm just going to show the hyperplane real quick. So that's separated out into above and below the hyperplane. So real quick, you may have heard of the use of kernels and support vector machines as the kernel trick. Almost always when you kind of start reading about support vector machines, everyone's like, oh, we use the kernel trick, project it to a higher dimension. I want to make something very clear though, because even I see this misinterpreted online a lot. The kernel trick is actually not projecting it to a higher plane. The kernel trick actually has to do with the mathematics of computing those points in a higher dimensional space. It has to do with a trick that you can actually replace the projection to a higher dimension with an inner product of the feature space that you already have. Now this goes pretty deep into math, so we'll leave this as another lecture you can revisit. I filmed the mathematics lecture in the course, so you can check that out. It's called Kernel Trick and Math. It's already in the course. I already uploaded it, so you can check that out. But essentially, the kernel trick itself is not the projection to a higher space. That is just using a kernel. The kernel trick is, in theory, I don't actually have to calculate x squared every time. I can use some complicated vector math and linear algebra to do all my computations in the original feature space. If you are interested behind the mathematics, unfortunately, I think it's going to be kind of too long to cover it here. I've already filmed this. It's called Kernel Trick and Math. And if you want, you can do the reading in Chapter 9. It kind of goes through some of the kernel trick. I should warn you, though, in ISLR, even they say that the full details behind a kernel trick are outside the scope of the book. If you really want the full details on how the kernel trick is working, you can check out the publication in 1995 called Support Vector Networks. And that is actually pretty well written for a layperson to go in. As long as you understand what a dot product is, you can check it out. Which course? The course that I announced this, it's 2021 Python machine learning. It's the support vector machine there. Okay, so we're kind of at a good spot for us to kind of switch gears and go into Python. I'm going to see if I have any questions here to answer. Could you use the distance from the hyperplane as a classifier? Place it in the middle and all the ones of certain distance classified as male. Matthew, that actually is what it does mathematically speaking. In fact, later on, I'll kind of just show you right now. If we continue this, this is the mathematics that I'm not going to go into. Otherwise, I'll spend an hour here kind of drawing out math. But your question is, can you do the perpendicular distance? There actually is a subject to the beta squares being equal to 1, so that the perpendicular distance is actually a measure of what class you land on. So good intuition there. Read Chapter 9 in ISLR, and you'll get the full details, or just watch me go through this lecture in the course. But I'll hop over to Jupyter Notebook. King Bach, I think we answered your question, right? Awesome. Okay, cool. Checking out for some other ones. So do we essentially apply the same function to each value? So King Bach, in theory, yes, that's kind of what it looks like. But if you go deeper into the math, you actually are not applying this. You're applying an inner product to your original feature space. But as I keep saying, kind of hand waving over this, you can read Chapter 9 as ISLR for the full details, or watch the math lecture in the course. Because it's kind of a long lecture. This would take me like 40 minutes to go through. Okay, a couple questions. Is the kernel trick random or sequential? I'm not quite sure what you mean by that. It's definitely not random. You specifically try out different kernels and then use cross-validation to check out the soft margins in that kernel space. So definitely not random, although I'm not sure I would have called it sequential either, depending on what you mean by that term. Is this used extensively in production? Yes. Support vector machines are one of the most powerful machine learning algorithms. It's kind of crazy how well they perform, actually. I got a question in a quiz, that difference between soft margin and hard margin. Well, hopefully now you know. Soft margin allows for misclassifications, or really, it allows for points to be inside the margin. What about using this for regression? Is it possible? Yes, it is possible. That was developed in post-1995. And it's kind of the same idea, and we cover it in the course. We have a support vector machine regression lecture series there. Last question here. When we are converting from 2D to 3D, what will be the third dimension? So you saw it could be like x squared plus x1 squared plus x2 squared. It depends on the kernel. The kernel itself will define what the higher dimension is. Are the dimensions selected from smallest to largest or randomly? I'm still not sure I understand that question. The dimensions themselves you shouldn't actually think of them as like x squared, x cubed. That's actually one particular kernel, the polynomial kernel. There are much more complicated kernels that are not going to relate to the way you think about x squared or y squared, etc. So just to show you what some other kernels look like, in fact, the most popular one is the radial basis kernel. The radial basis kernel looks like this, and it's actually not a x squared, y squared. It's a much more complicated function. And this actually could, in theory, this performs an infinite number of comparisons between training points to each other. So it's actually impossible for me to visualize this or even explain it with charts. You can just think of it as a mathematical operation that occurs. So it's kind of hard to answer the question, are dimensions selected from smallest to largest or randomly? That question, it's almost like irrelevant for what support vector machines actually do. It tries out a bunch of different kernels, tries out a bunch of different dimensions, and tries out a bunch of different soft margins through cross-validation, and then it figures out what they do. Now, is that random? Maybe not. It's kind of a grid of options to search for. Okay. Any other questions before we kind of hop over? I'm going to bring over my... Okay, yeah. So technically, Julia, in terms of polynomial kernel, yes, it's going to be try x squared. Try x squared and x cubed. Try x squared, x cubed, x to the power of 4, etc. So that's kind of a grid search going higher and higher until you find the hyperplane that can separate. In reality, though, you end up using much more complicated kernels where that's not even an issue to think about. You let the computer do the work. I'm going to start a new notebook, and you guys can do the same. Once we had one last question before we start. Don't we lose the correlation of each feature to the label once we do this transformation? Not really, because there's a relationship between, if there's a relationship between x and y, by definition, there's some relationship between x squared and y, just as there is some relationship between x cubed and y. Now, is that relationship as interpretable? Definitely not. Almost to the point where it could be meaningful or meaningless. But the idea is, on some other kernel transformation, there is a relationship that hopefully has enough signal that I can draw these hyperplanes that separate, allowing for some soft margin. Yeah. Some of these are actually mathematically impossible to do by hand. Specifically for the radial basis function, it's quite interesting. It does, like, in theory, it does an infinite number of comparisons. But only the computer can reduce that down using an inner product to the original feature space. So I'm actually going to copy and paste the data set one more time in case people missed it. Give me 1 second here. All right, so I copied and pasted the data. You can just download that. It should be a CSV file. Let me copy and paste this here. 1 second. And then I need to copy this token. Sorry. I have 2 windows, so I want this one open. And this other window, bear with me for a second. Okie dokie artichoke. So what we're going to do here is just go through a little bit of analysis of support vector machines for classification. And, oh, I think I need to give you... Oh, yeah, we're good. Okay. And, oh, did I close my slides? My slides do talk a little bit about this. Here we go. Yeah. Sorry, I'm going to scroll all the way down. Okay, so the project we're going to be doing together right now, and we're going to go through some parts of it, some parts we're not going to go through it. I just kind of want to explore this data set with you, and later on, if you can go back to the course and do the full exercise yourself. But for right now, what I want to show you is essentially, we're going to try to answer the question, can you detect fraudulent wine based on features from a chemical analysis? I had a quick question. Would you be discussing model maintenance after? Yeah, we'll have a section at the end of the course on, not the end of the stream, but at the end of the course on model production, model deployment. Okay, so for this stream, what we're going to do is we're going to answer the question, can you detect fraudulent wine based on features from a chemical analysis? And you can check out the actual Wikipedia page on wine fraud. So even if you just Google wine fraud, it should pop up. My internet's kind of slow. Copy link address. So that's I just pasted the link that I'm talking about. I guess you'll catch up and see what the heck I'm talking about. But here's what we're going to try to do. If you think about the wine industry and wine fraud, there's, as we all know, there's some super expensive wines, and we also know that there's some super cheap wines. And at the end of the day, it's all fermented grape juice to some degree, right? Or to every degree. And what we want to be able to do is, in the wine industry, some people try to pass off cheap wine as like historically very good wine or something like that. They essentially take their wine and relabel it as some expensive brand. Now I should note here, and you can check out the Wikipedia article on this, there are, technically speaking, different kinds of wine fraud. The most common one is actually just taking like grape juice and rubbing alcohol in it, shaking it and saying, oh, this is wine, or some kind of more advanced version of that, essentially kind of falsely making wine itself. But the kind of fraud we're going to try to solve here is someone is taking what is like an okay bottle of wine and they're relabeling it, repackaging it, and saying, hey, this is like a $2,000 bottle of wine. Look at the label. I'm going to sell it to you for $2,000 when it cost me like $50 or something like that. So we have a data set where people did chemical analysis on a bunch of wines that they already knew were fraudulent or real. And based off that chemical analysis, can we use support vector machines to classify something as a legitimate wine or a fraudulent wine? Fraudulent essentially being like a low quality, legitimate being high quality. So is this a like $2,000 bottle of wine, yes or no? So something to note here, and what I kind of really want to make clear, is you'll often get situations like this for machine learning, and people think like, boom, machine learning, this will be the cure for everything. Machine learning can solve this problem. No big deal. What I actually want to present here is this problem actually even solvable? Is there really that much of a chemical difference between a fraudulent wine that is a cheap wine versus a expensive real wine, so to speak? So keep that in the back of your mind. And what you can also do is do a Google search to see wine competitions that are like double blind. And almost always, whenever there's a wine competition where the judges were blind to the brand and what wine they were actually drinking, you'll see that very cheap wines perform better or at least as good as very expensive wines. And like I keep saying, at the end of the day, it's just grape juice that you let ferment. Not to get too much into the wine industry, but whether or not fermented grape juice can have such a wide price differential is more a statement of the industry and the people that buy these expensive wines than it is for the chemical analysis of what the actual wine is itself. So let's check it out. So what I'm going to do is kind of go through this with you and see if we can figure this out. So we're going to import a bunch of libraries. Let me zoom in a little bit here. And maybe if you have any questions as I jump to the notebook, you can let me know. It can be solved without chemical composition. You check the labels. But anyways, we'll discover that on our own. As PD, import Seaborn as SNS, import matplotlib.pyplot as PLT. So I'm just going to do my regular imports, NumPy, pandas, and then these two libraries for visualization. And we're going to use pandas to read in the data set. And kind of feel free to ask questions as you come along here. Right now, we're not really going through slides, so I think it's okay if you get stuck on a line or something. You have to pass in the file path to wherever you saved your CSV file. So I saved mine in a folder called data. So you may need to like pass in your full file path, like C, users, etc., until you find the folder. So I saved mine in wine fraud CSV. You should be able to tab autocomplete this. Okay, so what does this actual data set looks like? And as a quick note, the data set is from this publication. We do have a notebook that goes for this project. It's actually already in the course, so you can download it there if you want. But we're not going to be doing the entire project. We're just going to be kind of showing you how support vector machines could work in this. And then you can try the whole project where you can try out different models, etc. Okay, dokes. Where is my... Sorry, I'm looking at something on the YouTube streaming. Okay, good. Okay, dokes. So, notice here, I have a bunch of chemical analysis for these wines. The acidity, I don't even know what some of these are. Citric, sugar, that makes sense. Dioxides, density, pH values, sulfates, alcohol. And then I also have the quality, trying to predict whether it's legitimate or fraud, and then the type itself. So what I can do is say something like SNS count plot, and then say SNS count plot, data is equal to df, x is equal to quality. And this will produce the counts themselves. Maybe I zoom out one level. Okay, so something to note here is that I have a lot more legitimate wines, almost 6,000 legitimate wines, than I have fraudulent wines. And if you ever want to figure out the value counts for these, you can say df quality dot value counts, and it will actually count out how many you have. So this is what is known as an imbalanced data set. Almost always when you're dealing with fraudulent data sets, not the data set itself being fraudulent, but fraud is contained within the data set, it's almost always imbalanced, which is good because that basically means most people are good and fraud does not occur that often. So whether it's credit card fraud, wine fraud, or spam, etc., the vast majority of stuff in the world is legitimate and not fraudulent. So whenever you see a data set that deals with fraud, it's almost always going to be imbalanced. And we'll talk about different ways to deal with that. Support vector machines actually have a built-in way to do this with scikit-learn, and that is to add in a weight factor to value or weigh the fraudulent points more to try to pick up more signal from them. All right, so what we're going to do here is I'm going to show you how to build out a support vector machine model to try to classify wines as fraudulent or legitimate based off their chemical features. You can continue visualizing this, and in the course we do visualize this more, and we ask you to do more tasks than what I'm showing here. But for right now, we're just going to go through how we would perform support vector machine analysis on this. So what do we need to do here? I'm going to write out the steps. We need to split our data into a training set and a test set. Why do I do this? Because I want to have some sort of test set as a holdout in order to fairly evaluate my model. So hold test set for performance evaluation. What's the next step after that? Well, I should, actually before this, I need to make sure I deal with categorical data. There's one categorical column here. It is the type, whether the wine is red or white. I will need to deal with that data because support vector machines, they can't work with string data, right? They can't say, oh, let me fit this line to the word red. So I'll have to deal with that categorical data, essentially turn red versus white into zeros and ones. So once I deal with that, I can split the data into a training test set. Then after that, I'll scale the data. The reason we scale the data is because support vector machines, it's working on an analysis of dimensions, right? And if one feature has a different dimension, like way off than another feature, then the hyperplane is going to get really distorted on a certain feature versus changes in another feature. So we want to scale all the data so they're all around the same order of magnitude. That way the hyperplane doesn't fit too much to any particular feature. Instead, it kind of treats them all as equally important right off the bat before it tries to figure out which ones are truly important. So we'll split the train test split. Actually, before this, we will also have to say features X and label Y. We'll scale the data. Once we scale the data, we should be essentially ready to go to create a model. So we're going to say create a support vector machine model, and then train the model. We'll choose some hyperparameters. Train the model, and then evaluate model. All right, so that's everything we need to do. It's actually not too bad. First thing first, I just wrote them out so we can kind of go through it together. You can see where I'm at. Deal with categorical data, red, white. So as I mentioned, I have one issue before I can jump straight into machine learning training. It's this one, type, red and white. This one of quality, that's actually not an issue of it being legit versus saying fraud, because that's my label column, and scikit-learn can actually support string labels, so that's not an issue. What is an issue is if I want red versus white wine to be a feature, I can't pass it in as a string. So the way we do this is we say the following. I'm going to say PD get dummies, and then I can pass in, if we look at this, it takes in the data that we want to make dummies out of, and we'll see what the results look like in just a second. So if I say PD get dummies of df type, it automatically creates this Boolean for you. So it says red, white. So if the wine was red, it'll say 1 and white 0. If the wine was white, it'll say white 1 and red 0. Now, for those of you that have gotten to the machine learning section of the course, you actually already know that we do not need to keep both of these columns. I actually only need to keep one of them. Why? Because the information for white is technically already encoded in red. If red is 0, then we know it has to be white. There is no other option. So when we're dealing with these kind of binary dummy variables, I actually only need to keep one. This is such a common operation that there is a drop first parameter inside of get dummies that I can set as true, and it will automatically just drop the first column. And now I have successfully transformed the original df type red and white into a numerical column, whether or not the wine is white. So I'll do the following. I'm going to say df type is equal to this, essentially overriding this. Keep in mind, you should only run this cell one time, otherwise you're like dealing with problems. So be careful with that. Let's confirm this by checking out the head of my data frame. And did we accidentally drop it? Oh no, here it is, type. Okay, so type 0s and 1s. Perfect. So we're good to go on that. Let's give ourselves a little check mark here. So this one is done. Next, features X and label Y. I need to separate this out into features and a label. The label is quality, whether or not it's legitimate. Everything else is features. So we'll do the following. We'll say df drop quality column. X is equal to 1 to drop the column. If you see that, that's everything but the quality column. Those are my X features, which means Y is the quality column. Okay, so that's it. I have my features and I have my label. I have X and Y. I'll keep scrolling up here. Hopefully this doesn't bug you too much. But I'm just going to delete these as we finish the tasks. Split our data into a training set and test set. So how do I do this? I do this with the following way. I'll say from sklearn dot model selection import train test split. And what this is going to be able to do is train test split, do shift tab in a brand new cell. So after you import it and run that cell, you can do shift tab here. And if you've done any machine learning lectures in the course, you know what I'm doing here. If not, maybe revisit those and then come back to this live stream. But I'm going to copy this, paste it in here. And what this does is it creates a training set, a test set for both features and labels. For my test size, I'll go ahead and just choose like 10%, so 0.1. Random state, I'll go ahead and keep it as 42, not a big deal. I don't think that's what I do in the solutions notebook, but you can check out the rest of the lecture for that. Xtrain, okay, that's good. And that's all we had to do. So we'll come back here. And now we're done with split our data. And let me know in the chat if you have any questions on any of these steps as we kind of go along here. All right, almost there. Scale the data. How do we do this? We'll say from sklearn.preprocessing import a standard scalar. We create an instance of the standard scalar object. And the scalar, what it does is it's able to scale data. So if we take a look at scalar, we should probably be able to see it here. What it does is it operates this equation. Where are you? I guess it doesn't show you here, but essentially it uses the standard deviation to scale the data. Where is it? Oh. It's going to essentially calculate the z-score and then standardize the features by removing the mean and scaling to the unit variance. Essentially just a way of saying it's going to create all the features and put them around the same order, magnitude, and range. So how do we do this? We're going to say scalar.fit transform on xtrain. And I want to show you what actually occurs here. If I take a look at xtrain, notice the ranges of the features. Like total sulfur dioxide is at 162, density is at 0.99, right? So density clearly goes from like 0 to 1, and sulfur dioxide goes to much larger numbers. If I were to scale these, notice, well, it's kind of hard to read now, but notice now everything is much closer to being between -1 and 1. Okay. Should the split be higher? It's up to you what it should be. No, you're not making it meaningless, because it's not a multiplication problem. You're just saying if you make one of the features 0, essentially what you're saying is I have a feature that is either 0 or 1. So that does have meaning. It means it's either the beta coefficient that you're calculating on the hyperplane is either going to be multiplying by 0 or multiplying 1. There is signal there. It's not the same thing as 0 versus 0. Oh, and then the question is, shouldn't it be higher as there is data imbalance? I will actually let you guys play around with that. I just put 10% there. You probably would want to go higher because that only leaves you with like 20, in theory, any 20 points. But I should note that scikit-learn does stratified sampling. So it will keep the ratios of the imbalance the same on your training set and your test set. So if 10% of your total points were fraudulent wines, that means 10% of your training data will have fraudulent wines and 10% of your test data will have fraudulent wines, regardless of how you do the split. If you did a 50-50 split, 70-30, etc. I believe in the actual course we do a 30% split. We're essentially making it a little bit harder on ourselves to make a smaller split. Because we're not going to give ourselves that many instances of fraud. And then a question here, would you recommend using pandas get dummies in production? Yes, I would. Or use a scikit-learn equivalent. That's also up to you. There is one hot encoding. I use pandas get dummies all the time. It's essentially the same thing. I believe they're both actually performing the same NumPy operation at the end. What I like about pandas dummies, it has that drop first already built into it. Okie dokes. So we are going to now scale this, where we'll say scaled xtrain is equal to this line of code. And then I'm going to say scaled xtest is equal to this line of code. Notice I'm only going to fit to the training data because I don't want any prior knowledge of the test data leaking into my operations. I don't want to assume any prior knowledge of the test data, even if it's something as simple as the average value or standard deviation. So I have my scaled version of train and my scaled version of test. So we're going to come back up here and knock that off our list. Scale the data. Okay, so SVC choose hyperparameters. And this is where I think different people are at different spots of the course. So I'm going to manually choose the hyperparameters. In real life, you would not do this. You would use a grid search. But we actually have many sections of the course kind of discussing grid search, how we go from train test split to cross-validation to grid search, etc. So that's kind of like an hour-long discussion if you've never seen it before. If you have seen it before, you can just check out the notebook that goes along with this lecture inside the course, and we do ask you to do a cross-validation. So just so you know what I'm talking about, I'm going to bring in the notebook that I'm kind of working and following right now. So in the project, if you go to the course, we will actually ask you to run a grid search with cross-validation and test out a bunch of different C values for soft margins, some gammas, a bunch of different kernels, etc. For right now, though, I'm going to just manually choose the hyperparameters, and we're going to see how it performs, and then we'll kind of play around with some hyperparameters there. In real life, you would never do this, but I think based off the comments I saw on the educational announcement inside the course, people are at varying levels into the course. So some people are just about to hit the machine learning section. So if you're just hitting the machine learning section, you might not know what cross-validation is at all. In which case, I don't want to kind of just like throw it in here when choosing hyperparameters manually. It's kind of really clear what I'm doing. So maybe you guys can tell me in the chat whether or not you guys reached the cross-validation section already or not. But what I'm going to do is I will just manually choose the hyperparameters. So we'll come back down here. I need to create a support vector classifier model from sklearn.svm, which stands for support vector machines, import capital SVC. That is the support vector classifier. And I always recommend just whenever you're dealing with a scikit-learn model for the first time, go straight to its documentation page and open it up. You will find that incredibly useful. So I'm going to copy and paste this. And let me put it up in here. I'll take you to that page. While I'm waiting for this to load, I had a quick question. I guess if that's happening for you, Neil, that your code is breaking, use scikit-learn's one-hot encoder and then build a pipeline around it. That way you just never have to deal with that issue. Especially if you have like issues with like new factors coming into play. Okay, so support vector classifier, the bad boy of machine learning. So what do we have to do here? Recall that I mentioned there's different kernels we can choose. We chose a polynomial kernel in our examples, but the actual default kernel is something called as the radial basis function. It's a much more complicated kernel, but it performs pretty darn well. We also see the C value. The C value is essentially how soft do you want these margins to be. I should note here that something that's kind of annoying about scikit-learn is a lot of times these regularization parameters, basically how soft the margins should be, they're inversely proportional to C. What does that actually mean? It means if you open up Introduction to Statistical Learning and you read about C, the higher C is, the more points you allow within the soft margin. Scikit-learn, because it wants all algorithms to be as uniform as possible in what you're actually passing in, it makes this C inversely proportional to the C you see in the actual equation, like on a Wikipedia page, etc. So just keep that in mind. The kernels we have to choose from, there's a linear kernel, that's essentially just like a straight line. Polynomial kernel, that could be x squared, x cubed, etc. Radial basis function, sigmoid, and then a pre-compute. For the polynomial kernel, recall I said you could do x squared, x cubed, x to the power of 4, etc. That is where the degree argument comes into play. So if you did choose a polynomial kernel, you should also tell it what degree you want to actually explore. So it is ignored if you're choosing another kernel. So what I'm going to do is let's choose the polynomial kernel. Let's choose a default degree of 3. And I'll also choose the default C value. Whether or not that's good, we'll have to see. All right. So I'm going to create SVC is equal to a version of VC. And I mentioned I want my kernel to be a polynomial because that's what we saw in the lecture. Whether or not that's a good choice, we'll kind of ignore that right now. Let's go ahead and do a 4th degree polynomial. Give us a little extra juice, who knows. And then what did I also mention? Oh, my C value, we'll keep it as the default 1. And there's one last thing I wanted to mention. I keep saying these are imbalanced classes, right? If we scroll back up here, there's way more instances of legitimate wine than there are fraudulent wine. Something you can do, and many scikit-learn classes have this built in. There is a class weight parameter in a lot of classes. And if you scroll down, it essentially explains what it's doing. And we talk about this in more detail in the course. But it tells you that you can actually weigh the classes proportionally to how much they show up in the test set. And it does this through this calculation here. So essentially, if I say try to make this balanced, it's going to balance out the weights of the instances of the classes. So what does that actually mean? It means if you have a class that has a very low frequency, it's going to add a weight, so to speak, just to make the signal a little stronger there. To say, hey, you should pay attention to this class a little more because there's not too many instances of it. And it does that proportionally. So that means if it shows up like 1 over 10 times frequency, so 10% of the time, it will try multiplying it by around 10. And you can see the calculation that's being done here. Hopefully that makes sense to everybody. It's essentially just add a weight proportional to how balanced or imbalanced the class is. If you had a perfectly balanced training set, even if you said class weight is balanced, it wouldn't do anything. All right, so balanced. That means by default it's none. Since my stuff is imbalanced, I need to say try to make this balanced. Essentially try to make the weights that you're applying to this balanced. So we'll say, whoops, class weight is balanced. That should be a string. There we go. All right, almost there. I think I'm still at the step of creating the model. So I just chose the hyperparameters. I want to train the model and evaluate the model. So I chose my hyperparameters a little bit in a la-di-da fashion, but that's okay. You can check out the lecture video on this for seeing how I do full cross-validation. Now what we're going to do is I'm going to say SVC, and I'm going to fit it to my training data. I have to fit it to my scaled training data, don't forget. Scaled xtrain, ytrain. It's going to run that. It tells me, hey, you just ran this model, and I fit it to this data. Now it's time to get some predictions. So how do I actually do that? I say my predictions are going to be equal to svc dot predict off the scaled x test data. And so now I see my predictions as legit or fraud for the features in scaled x test. Recall that I also know, I'm not going to scroll down here. So I have my predictions, legitimate and fraud, and I have the correct answers, right? I have y-test, legit or fraud. Let's see how poorly this model actually performed. It may just suck. I'm not sure. This is not what I used. I used a radial basis function in the lecture notebook, so fingers crossed this actually is able to classify anything. It may just classify everything as legitimate and we're totally screwed. We'll see. That's a very common problem with imbalanced data sets. So how do we actually evaluate this model? Many different ways we can do this. I'm going to use a confusion matrix and classification report, probably the two most common ways to understand this. And if you don't understand what these metrics are, accuracy, recall, precision, check out the course. We have pretty extensive lectures explaining each of these metrics. We'll say confusion matrix and the classification report. All right, fingers crossed. I think this might perform horribly because I chose pretty bad examples or hyperparameters. Let's see, y-test against predictions. Oh, that's not so bad. Okay, and there's actually a really nice function that I'm actually going to import here called plot confusion matrix. So that's right here, plot confusion matrix. We show this in the course as well. I mean, everything I show here we show in the course, and more. So I can actually call plot confusion matrix. And what's nice about this is it actually takes in the model, the scaled x test data, and then y true or y test. So I can say scaled x test. Oops, I have to first pass in the model. I can say SVC, scaled x test, and y test. So it actually does the prediction part for you. So why is this nice? It basically plots out this in color. Okie dokes. So we're actually kind of done, but we have to answer that question. Is this actually possible? Is this useful? What am I saying here? I have my predicted label and the true label. This is why you should probably plot this out. It makes it easier to read versus this right here. Okay, recall I want to find the fraudulent wines. So in my test data set, it looks like I had, let's see, 25 fraudulent wines, right? I had 13 and 12. Add those together, that's 25 fraudulent wines. The true label is along this direction. So out of the 25 fraudulent wines, I found 13 of them. That's not bad. But it did come at the cost of me saying 53 legitimate wines were fraudulent. Is that good or is that bad? We'll have to calculate the precision recall with the classification report. And you'll have to discuss this with like whoever the owner of the restaurant is or whatever, whether or not that's worth it. Essentially, this would say, hey, these 13 and these 53 wines, because remember, your model's not separating this out. Your model just says, hey, I found 66 wines that I think are fraudulent. That would indicate to the person running this model, hey, you're going to have to take a closer look at these 66 wines. Call your supplier. I think we have a case of fraud here. Now, is it true for all of those? No, it's actually only true for 13 of those. The bigger problem is, you're actually, if we take a look at the predicted label for legitimate wine, most legitimate wines are actually getting through as legitimate. 572, that's not so bad considering the imbalance of our data set. But there's going to be 12 wines that sneakily got away from our algorithm. But we can still play around with the hyperparameters of the algorithm to see if we are able to find those or not. Main thing to note here is more or less the fraudulence, about half of them are getting caught, half of them are not getting caught. You can think of it that way. And one way to do that is to say print classification report on, let's see what comes first, y test versus predictions. Okay, so remember I said that more or less half the time you're getting fraud and half the time you're not. That's actually what's being shown here for the recall of fraud. About half the time you're able to figure out fraud. Is that good? Is that bad? I don't know. It's better than the alternative of doing nothing. But you do have to understand it is implying extra work of having to now figure out if these 53 wines were actually fraudulent or not. But this is machine learning, right? This is real life of how well these models can actually perform. So that again brings up the question, is this actually worth it? Is this good? Well, one thing, we have to take a step back, try other models, try other hyperparameters, see if we can improve this performance. Once we think we're optimally performing on this data set with whatever model or hyperparameter we choose, then comes the time to ask ourselves, is this good enough? Is this worth it? How much of a problem was fraud in wine? Is it worth testing 66 bottles of wine to find the 13 that are fraudulent? And when I say testing, I mean, checking the label, doing stuff outside of chemical analysis. What is nice is that hopefully running the chemical analysis and running the machine learning model on a new bottle of wine is not as invasive of a process as doing all the background research of like checking the supplier, checking the data, etc., the shipping records, etc. But hopefully this gives you an idea of what is possible and what you can do with this project. As a quick note, this project should now be part of the course. We go into much more detail than what we see here. If you go to the last section of the 2021 Machine Learning Masterclass course, it's up now. So just to show you, I guess this is what it would look like for someone that's not enrolled in the course, but everyone in this chat should. Good question. How many different models would you recommend we try? Minimally. Uh, One answer is as many as it takes. It would be maybe what your boss says if he's not a very good boss. He says, whatever it takes, find a model that works. Um, what I would say is try at least 3 models that do not operate on the same, how should I say this? On the same set of like mathematical principles. So typically what people like to do is a random forest, maybe a support vector machine, and a logistic regression. Those are all 3 classification models that operate on very different sets of mathematical principles. One is kind of doing a logistic curve, figuring out the best parameters there. Random forest is making a bunch of decisions per feature. And the other one, Hyperplane, is kind of projecting this out into higher dimensions. Now, Neil, if you were to try all 3 of those and you get similar results, that's actually good because that's telling you, hey, regardless of what model you throw at this data, you're kind of hitting the maximum optimal performance that's possible. But I would probably say 3 models. The problem is, if you try 3 models and they all get you wildly different results, 1, take a look back at your data, see if there's something weird going on there. But 3, try different models because that means certain approaches are much stronger for this data set than others. That is more unusual that they give wildly different results. But if they do give similar results, that's good. That means that you're kind of, no matter what you do, you're starting to hit the peak of what's possible with the data. So I just want to bring this out here. You guys should, I would imagine everyone's enrolled in this course, otherwise how would you have gotten this message to visit this stream? But I wanted to point out support vector machines. There's a lot more to it than what I just, 2 hours. We talk about history, we talk about kernel trick mathematics, classification, we do a regression, and we do the project itself. So you can scroll down to the bottom of the course and check that out. With neural networks, no. In fact, neural networks are definitely not overkill. That is literally what the original publication that has this data covered. So if I Google search this publication, I believe I'm pretty sure this original publication actually used neural networks. Neural networks, I would say, is not overkill for this data set. Granted, it depends how important wine is to you, but yep. Okay, and that's pretty much it for today's stream. I know you guys sometimes lag a bit, so I'm going to wait a couple of seconds for any last questions. Type out, thanks everyone. Any last questions I can answer? I can see labels help to classify, but again, features have chemical compositions. If someone is doing fraud, he will put incorrect chemical composition. Basically, what we have to realize here is that fraudulent wine chemically looks a lot like legitimate wine. One way to think about this is don't think about wine, but think about bottled water, right? Some samples of bottled water are way more expensive than other brands of bottled water. If you do a chemical composition on them, it's very likely they're going to be extremely similar, right? So we can almost think about it that way as like, try to find the fraudulent bottle of water, like your cheap brand versus your expensive brand of bottled water. And if you were to do a chemical composition, it'd be like they look exactly the same. Well, in whiskey industry, in theory, there's not going to be a barcode on the fraudulent wine that says, hey, I'm fraud, check me out, right? So the barcode is to try to prevent fraud, but the idea would be the fraudulent at that point would be, that's basically what you'd have to go check at this point, like, oh, is there a barcode on this bottle of wine we can check? Will oversampling the data set any methods help in improving? You could definitely try that, but in general, I would recommend doing the class weight thing first before you start oversampling. Just because oversampling could get you good results on your test data set, but when you actually deploy it in the real world, you're not really able to oversample again. So, it is what it is. But you can definitely try it. It's a common and legitimate approach for imbalanced data sets. Okay, I don't think I'm seeing any more questions here. I know I'm kind of a little behind. Can we get access to the video recording and notebook? You actually already have all that. It's inside the course, as I mentioned. Yeah. And Patricia, you will be able to do this because if you take the entire course, we build up to this gradually. We don't just jump in like this. But this everything I just covered, the notebooks are in the course. They're already uploaded. This recording will be available on the YouTube channel. And I have set recordings of this same project inside the course. So you'll have access. You already have it. I should say, not you will have access. You already do have access to all this. Thank you. Thank you. Any other questions before I sign off? Okay, I'm going to end the stream. Going to I'm just going to wait a couple seconds here, make sure the stream is ended, since there could be a delay. Okay, oops. All right, thank you, everyone. Thank you so much. I'm going to end the stream. Thank you. And hopefully we have something good for you next week as well, as I had to take a break for Thanksgiving. All right, I'll end the stream now.